Algebra 2, lecture 2. Yes. You like it? No, no, no being cynical. Yes. You prefer writing links? No, no, this one. If you prefer the links, we can do it every week, every lecture, including Infi, including calculus if you want. I'm just a bit tired of this wound. A lot of antibiotics I take. Should drink Actimel. You know what Actimel is? Yes. To drink some. Oh, wow, wow. Yes. That's what I was afraid of, but write it down and copy to another day. It'll be fine. Okay. So let's put it underline and start. I can, make it bigger, smaller, the font, whatever you like, the tone. A little reminder. We define the concept of determinant. Define the concept. Hello. What you having there? Oh, I'm already fat. We define the concept of determinant of a matrix n on n using permutations. I don't think with the very big delay we had before we started that I want to remind you what permutation actually is and how we define with permutations. We saw that determinant of a triangular matrix is the multiplication of the elements of the diagonal. Moreover, in addition, we saw how elementary Watson row operations affects the determinant. So let's remind this as well. Most importantly, again, most important, adding row or multiplication of a scalar and a row to a different row doesn't or isn't changing or doesn't change, does not change the determinant at all, which is very nice, as we saw last week, because when it comes to eliminate using Gauss elimination or something similar to get a triangular matrix, we mostly use these kind of row operations. So one can calculate the determinant of a matrix by getting it to a triangular matrix using elementary row operations and understand how these row operations change the determinant. And again, when we only use the adding a multiplication of a row to another row, we don't affect the determinant at all, stays the same. So we do have one way of calculating the determinant, eliminating and multiplying the elements of the diagonal. A different, let's I just want to see, you see me there, talking up, right? After we wrote all this stuff and we had an example of calculating the determinant, I think it was a matrix 3 on 3 from 1 to 9. Those were the elements. We wrote some of the determinant properties. Properties. First of all, it is not additive, but it is multiplicative, meaning that the determinant of A, B is determinant of A and determinant of B. When the determinant is defined, as we mentioned last week, if you multiply, for example, a matrix 3 on 2 and a 2 on 3 matrix, you get 3 on 3 matrix. In this case, the determinant of A, B is defined, but the determinant of A and B alone are not. So when it is defined, you can write it that way. What else? What else we thought about the determinant when we multiply a determinant we multiply the matrix with a scalar, the scalar goes out to the power of the order of the matrix, because we multiply every row with A. If you have n rows, you multiply by A n times, which is A to the power of n. What else did we mention last week? I think that's all. Oh, from A, one can get, generally speaking, the determinant of multiplications of many matrices, not just one, is the multiplication of the determinants. Again, and here, from C, one can get, one can get the following statement. So let's have a space of row and we start our new material. Colorally, how do you say maskana? Colorally, maskana. Okay. Conclusion, no, different. I have a different fancy word, but I just remember how to say it correctly. Let's use Google. Follow. No. Corollary. Corollary. That's it. That's the right word when it comes to text in mathematics. So, write it down. Corollary. I in my head corollary. The R and L. Corollary, if A is invertible, then the determinant of the inverse matrix is the inverse of the determinant, which means when it comes to numbers, one above the determinant of A. If any of the lines is too thin, unclear, just tell me. I think I can improve it. Let's prove this corollary, all right? It's fancier than conclusion, you have to admit. What is the connection between A and A inverse? We know that the multiplication is I. And so the determinant of the multiplication is the determinant of I. Now the determinant of I is 1 because it's a triangular, even diagonal matrix. So the determinant is the multiplication of the elements of the diagonal. And on the other hand, when it comes to the left part of the equation, we have a determinant of multiplication of matrices, which we can write as the multiplication of the determinants. And so we can divide it by the determinant of A to get our corollary. Let's save it for the computer breaks or something. In the first or the second semester after the corona broke through to our lives, I was writing down in the lecture through the Zoom. It was 4 hours lecture in summer semester, and in the middle of the 4th hour, the computer just had enough. went down, and all that I was writing for almost 4 hours just to the pach. Now let's save it. New file name, folder. It is Tafshin Peivav, current year. And let's call it linear algebra, lecture 2. Now let's full name. Algebra 2, lecture 2. Elad. Tafshin Peivav in English would be 5786. Okay. You can write it down with spaces. If you do know leaks and you tried it sometimes, getting a good, nice PDF from the leaks may be problematic sometimes. You have to write down the right kind of names to the file in order to do so. For now, it will not give me a PDF, even I tried my best. I think I just copy it to a different type of leaks templates and hope for the best. Now, after I wrote down this corollary, what I want, first of all, questions? Okay. All 6 of you are here, so nobody in the Zoom except me. I'm here twice. One for the computer, one for my computer. We already lost about 20 minutes in the beginning, and I don't want to okay, shut up. I don't want it to take very long besides the delay, but I do want to mention it. How do we prove all these statements, all these properties of the determinant? Some of the proofs goes to the basic, to the definition with permutation. As we mentioned last week, we didn't write down any proof like this, but we do talked about it. Hey, if we multiply a row by a scalar A, then every element is multiplied in the row is multiplied by A, and every element of the sum of the definition with the permutations is multiplied by A, and so the determinant itself multiplied by A. For example, something we said last week. But right here, when it comes to the more, let's say, complicated statements of the properties, for example, the determinant is a multiplicative function, in order to prove such properties, such statements, one need to use the concept of the elementary matrices. I want to remind you, it probably was in the first course, and you, as I recall, you told me you had much fun in the first course, so you probably be very happy about this reminder. Let's say it's note or something. It's not very important. Ah. Want to do it that way. Very nice. Note. You have a better name for הערה in English? So we'll stick with note. In order to prove some of the properties we mentioned, one probably needs to use elementary operations or elementary matrices. Let me remind you what an elementary matrix is. An element for every new row, for every, oh, just every row operation has a corresponding, that's the right word, corresponding matrix called the elementary row operation matrix, or simply elementary matrix. Let's use a notation. Every operation, I use the Greek letter rho, and the elementary matrix operation, the note with rho of I, which is the matrix we get from the unit matrix I after applying rho. And for every order 1, 2, 3, etc., we have such matrices. For example, doesn't it go down? Okay. For example, let's get down a couple of words. For example, if say row is the operation of switching R1 and R2, left, right arrow. And we talk about matrices of order 3, for example, then row of I is the following matrix, 3 and 3. I is 1, 0, 0, 0, 1, 0, etc. But we switch the first and the second row, so one gets this matrix. I'm used to the Hebrew leaks where left is actually right and right is actually left. And here when I press the left button, it goes left, surprisingly. So it takes time. This row of I, generally speaking, one can write row of A, which is the matrix A after we applied the row operation. What is so important about uh, these matrices of the elementary matrices is that they are actually performing as row operations. Meaning, instead of taking a matrix A and apply some row operation, that's all fine. Hope you are fine. One can just one can multiply the matrix A with the corresponding elementary matrix and get the same result. And if we denoting row A, another difference between Hebrew leaks and English leaks. In Hebrew leaks and English as well, the formulas themselves are written in English. So I'm used to Alt Shift whenever I enter a formula. But here I don't need to Alt Shift. Denoting row A, the matrix we get from A after applying row. One advantage, sometimes it is important, of the leaks, one can write Control C, Control V sometimes without working hard and writing everything from start. If we're denoting row A, the matrix looking from A after applying row, then row A is actually row I multiplied by A. Yet again, come again. Instead of applying the row operation, one can multiply the matrix with the corresponding elementary matrix to the same row operation, of course. This fact is used when proving some of the properties and claims about invertible matrix, for example. Who was teaching linear one? Erez, the Sheikh. Best lecturer probably in all of Bar Ilan. So probably saw it when it comes to proving statements and stuff about invertible matrix, for example. As I mentioned here in note, in order to prove some of the properties we mentioned, one need to use the elementary matrices. I'm not going to go back and prove one of these statements, properties, etc., with the elementary row operation matrices. I do want to state a new property of the determinant and to prove it with the elementary matrices. Reminding you that I'm trying to follow these notes from last semester, Tafshin semester bet. It's in Hebrew and I write English. See what we can do. So what is the property I want to prove using these matrices? It's the following one. I ask you again, is there a better? No, whatever. That's a proposition. Proposition is good. And corollary is the maskana. Proposition, the determinant, let's write it fancy. Let A be a matrix of order n, whatever the field is. One can think of it of R or the complex number. I'm going to do some fancy examples. Let A be a matrix of order n, then I want the point to be outside. Then the determinant of A transpose is the determinant of A. Using transpose, meaning every row becomes a column and vice versa, the determinant stays the same. Okay? One can write a simple example if you want, but I don't think it's really important right now. What I want to say is when we use it, we can prove it when it comes to an elementary matrices, to mention here, and with the proposition about elementary matrices, one can prove the general one about matrices, just matrices. So, first, let's say prove down. First of all, or firstly, we prove the statement, the proposition for elementary matrices. So let row be a row operation, and we want to prove that the determinant of what was Hebrew? The transpose of row I and determinant of row I is the same. We have three different types of row operation. So we'll deal with every case separately. First of all, let's say we have the switching between rows. Yeah. So we deal with every type of row operation separately. That's how you write it. Separate. Too much A's. It should be E somewhere. Separately. Or it's good. Yeah, whatever. Like this. Okay. Let's write 1, 2, 3, whatever. One, we have row is switching rows. And remember, row I is not just general matrix. It's a very specific kind of matrix when we took I and we applied row on I. We have an example here. Yeah. So what actually happened if we take the matrix row I and we transpose it, we do the little t in the power. What I want to say is that row I, when row is switching, an operation of switching rows, is a symmetric matrix, which means that when transpose doesn't do nothing, doesn't do anything or do nothing, does nothing. Let's write it down quickly. In this case, the matrix row I is symmetric. Let's elaborate, but not so much. If you have the matrix, I itself is of course symmetric. The matrix I itself is, of course, symmetric. And the switching of two rows takes the ones of rows I and j from the diagonal and plugs them in ij and ji, I mean the entrances in the matrix. For example, if we applied here row 2 and row 1 switching, then the ones of row 1 and row 2 goes to the places 1, 2, and 2, 1 in the matrix. And generally speaking, when you switch row I and row J, the one goes to IJ and JI respectively. What? It's gonna be the same. Let's say the operation is, as you said, row 3 and row 1. So you apply it on the identity matrix. Let's write it down together. This is the identity matrix, and now you switch row 1 and row 3. So one gets this matrix, and as we said, the ones of row 1 and row 3 goes to 1, 3, and 3, 1, the places in the matrix. So such a matrix is still symmetric. And so the matrix, Hebrew, row I is symmetric as well, meaning the transpose does nothing. Therefore, same matrix, of course, the same determinant. Have some spaces, will be easier to read afterwards. After we finish, not no, the exactly 2.5 or whatever we finish, whenever we finish, I'll make a PDF out of this and I'll send it to you. Can't do it with the board yet. Sometime in the future, we'll probably have some smart boards like Tony Stark and stuff, moving with the hands, etc., etc. And specifically, we can pull out a PDF from the board, but right now we still don't have it. You can ask their calculus typically just put it on both drivers. Does what? What he usually does is he works on Word. Word. And he puts it. It's a very plebeian, but okay. Yeah. He puts it in a that's connected to Google Drive. No, how to send you the PDF? No problem. Now, the problem with leaks is that not everyone has leaks installed on their computers. And, leaks version 2.3.1 is not as 2.3.11. It doesn't work. It does work. I'll send a PDF. Okay. Second type, any questions? Okay. Second type, comments, whatever. Second type of row operations will be multiplying the row with some scalar A. So Ri goes to alpha or A, whatever, row I. In this case, the matrix row I is also symmetric. We have a diagonal matrix and we multiply one of the ones with A. It's diagonal matrix. Of course, it will be symmetric. Huh? Because we talk about the transpose. And when the matrix is symmetric, transpose does nothing. So not just the determinants are the same. The matrices themselves are the same. Again, the matrix row I is symmetric. So row I is the same when you transpose it, when you don't. And we get our proof as well. Let's add that it is even diagonal. Just multiply one of the ones with A, as we mentioned. And our favorite type of row operations, adding ARJ to RI. Operation from the identity. Yes. Yes, for a general matrix A. First, we start with the proof for the elementary matrices, right? That's our third and favorite row operation. Um, here we get the following matrix. We have ones in the diagonal, 0 outside the other diagonal, but in the I psic j entrance in the matrix, we have A, because we added 1 multiplied by A to the row Ri. In this case, we get the following matrix. 1 in or on, whatever you say, in the diagonal, 0 elsewhere, except the IJ entrance IJ place, whatever, which is A. Let's use our matrix here as example. Let's say we take R3 and we add 3 times R1. No, let's do another number, 4 times to R3. So let's get back to the identity matrix. Four times R1 to R3, it is 4 here. The entrance, the place, 3, 1 in the matrix is 4, it's a scalar A. In this case, the matrix is not symmetric, but row I and row I transpose are both triangular. Here, the 4 is under the diagonal, and when we do transpose, it goes here up the above the diagonal, but it doesn't matter because the determinant of a triangular matrix is the multiplication of the elements of the diagonal, and they are the same. The elements of the diagonal in row I and in row I transpose, and actually for every matrix A it's true, A transpose and A have the same elements on the diagonal, so we get the same multiplication, we get the same determinant. So row I okay. Row I is a triangular matrix, and we know that the determinant is the multiplication of the elements of the diagonal, main diagonal, or whatever, which is 1. Because on the diagonal we have just 1, 1, 1, 1, 1, 1, 1. Similarly, if that's how you write it, the row I transpose is triangular with nothing but 1 in the diagonal, meaning the determinant of row I transpose is 1, 1, 1, 1 as well, which is 1. Well, we do get determinant of row I transpose and row I determinants are the same. So for every elementary matrix, our proposition is true. You do transpose, you do nothing. It's the same determinant. Any questions?
So because it's triangular, the element that's so okay. So we we do the operation and go metric the
When it comes to the determinant, it is. For both of them are triangular, so we look only at the elements of the diagonal. And they are the same when you transpose one matrix.
yeah. You know other operation other than this one for now.
Yes, but these are the 3 types of elementary row operations. So for every row operation, for every elementary matrix that represents a row operation, we know that the determinant of the transpose is the same as the original one. More questions? So that was this is firstly, yes. Now let A be a matrix of order n. We have two cases. If A is invertible and if A is not invertible. The simpler one is if A is not invertible, then on one hand, we know that determinant of A is 0. We explained it last week. When you start using row operations in order to get a triangular form of A, when A is not invertible, you somewhere along the way get a row of zeros. When you have row of zeros, the determinant is 0 because every element of the determinant, the sum, the definition, contains one element from this row of zeros. On the other hand, we know that, and that is some knowledge from linear algebra 1, which was very fun. We know that if A is not invertible, A transpose is not invertible as well. So the determinant of A transpose is also 0. And we do get, they have the same determinant. And for our last case, what are you going to do when A is invertible? Here, I'm going to use the concept of elementary matrices. If A is invertible, speaking the language of elimination, we know that we can apply some row operations in some order, and we get the unit matrix I, the identity matrix. Now, talking in the elementary matrices language, it means that we can multiply A with some row operation elementary matrices and get I. If A is invertible, there are row operations row 1, etc., etc. Let's say row M, such that A is actually taking the matrix I and multiply it by applying the first row operation on I, which actually means multiplying it by the corresponding elementary matrices, matrix, etc., etc. Not N, I used M. To the last elementary operation matrix. Now, what we get when we are applying, when trying to calculate the determinant of A transpose, We have the determinant of all this nice, beautiful multiplication, I suppose. Nice, beautiful multiplications. We have the best multiplications all over the world. Nobody knows about multiplications better than me, better than I do. How do we apply the transpose on a multiplication of matrices? Every matrix gets a transpose, but we change the order in the multiplication as well. Specifically means that we have I transpose and row 1 I transpose. Etc. Good. Row 1 transpose. Now, write down. What?
How will we put there the same?
Yes, so we have multiplication, a determinant of a multiplication, which we know is equal to the multiplication of the determinants. So we have the determinant of I transpose and the determinant of row I transpose, and so on and so on, and the determinant of row mi transpose. Now, for every elementary matrix, we already proved that the transpose does nothing, and it's actually the same as the same determinant. We can cancel all the transpose from every determinant. Now the multiplication is between numbers, scalars. Every determinant is a scalar, of course. So we can change the order of the elements in the multiplication as like, and we like to change it in a way it will give us eventually the determinant of A. So I change the order of the determinants here, writing firstly row M, and lastly row 1, and determinant of I, whatever, it's 1, but let's keep it that way. Page up will kill me someday, but not today. And now, let's down in the bit, see it more clearly. We have yet again a multiplication of determinants. You can write it as the determinant of the multiplication. And the multiplication is how convenient, A itself. So we get, so finish line, the determinant of A transpose is the determinant of A for every matrix A. And proving this statement, we used the concept of elementary matrices. Any questions? Yeah. Generally speaking, as a lecturer, as the one who writes the test, the final exam, I don't really like questions of prove this statement you already seen in class. I mean, I did it one time. What should do it again? I know the proof. I like to ask about different statements, but can ask about a similar statement you will have to prove it using the elementary matrices. Not that I specifically ask you to do so, but it's because it's the only way. And yet again, we can many of the statements or properties we just mentioned without proving. If one wants to prove them, we need to use this concept of matrices, elementary matrices. For example, the the fact that determinant is multiplicative. In order to prove it, one needs to use uh, elementary matrices, and so the concept of proving a statement about determinant using the elementary matrices is important. Important. It's not a lifesaver, yeah, but talking about it in algebra too.
I feel like the most interesting result of this, I mean, not the result of self notion is that you can get the transpose of a matrix by multiplying the transpose of the elementary operations of the matrix. I mean, makes sense.
Yes, one can say so. It's a linear algebra 1 statement, but you can it's true. I'll repeat for the nobody's in the Zoom except me twice. For anybody will someday watch the recording. We have here, um, by the way, one can see that A transpose is the elementary matrices of A when you put transpose on each one of them. Yeah. And of course, changing the order of the multiplication. Yes. Yes, the statement is the determinant of A transpose is the determinant of A. They are the same. So we use, firstly, we prove that it is true for elementary matrices, meaning determinant of row I is the same as the determinant of row I transpose. And then we used this knowledge to prove the general statement about a matrix A. We used two things. That one about elementary matrices, and the second one is the property of the transpose, where the transpose of multiplication is the multiplication of the transposes, but in a different order. It's ordered backward. I want to write down one last corollary. We found the word earlier from this, and then we can have our 15 minutes break. When we come back from the break, I'll show you more convenient way of calculating the determinant, and then we'll move on. Where's the word? Here it is. Yes, corollary. All right, come on. Huh? It's like it's a statement that is proved by the last one we mentioned. In Hebrew, we say maskana. I don't have, I can look for different words for the word maskana. Proposition is te'ana. It's not maskana. Result is more appropriate, but result is totza'a. It's not maskana exactly. Google Translate says conclusion, but conclusion is more of sikum. But you can have maskana from the maskana. You can have a corollary after the corollary. Let's see different words he proposes. Ah, culmination, cessation, fancy words. No, no. Let's not worry ourselves too much. Manifesto. It's a proposition that comes straight from the last proposition statement proved we did. When, what did you say? When calculating the determinant using row operations, as we did last week, in order to get triangular matrix and such, one can actually use column operations as well. The determinant of A and A transpose is the same. The rows of A transpose are the columns of A. So we can take A and switch columns, multiply a column by some scalar, etc., because these column operations are actually row operations on A transpose. And when it comes to determinant, A transpose and A are actually the same. So that's one technical corollary, right? Come on. I wanted to mention. Huh? Yeah, yeah. Any questions? As I said, multiplying a column with some scalar, switching columns. Same as rows, but with columns. Because when it comes to determinant, transpose of the original are the same. Yes. And when it comes, for example, for solving a system of equations using matrices, it is not a good way to do it. Because changing the columns, changing the variables, which is not true. Right. But specifically talking about determinants, it is fine because A and A transpose and the rows of A transpose are actually the columns of A, and vice versa, are the same. They have the same determinant. No, no, generally speaking, we proved it for invertible and non-invertible as well. The statement A transpose and A have the same determinant is true, is always true. Okay, it's a good time, excellent time actually, for a 15 minutes break. So let's stop the recording, and you should remind me to after no, yes, to the club after our break. So as I mentioned before we got out, I want to talk about nicer formula for calculating determinant. Here, the way we actually calculate determinant right now, it's not a formula, it's more of a process. We get to the triangular matrix, and then the determinant is the multiplication of the elements of the diagonal. Here I want to show a different formula. It's not very necessary, but I'll call it after Laplace. Then dead French dudes is more of a calculus thing, but we have Laplace here as well. So I'll show the formula. I'm not proving its correctness. If we did have the time, let's say 4 hours every week, I would have shown you the why is it true. But we are not mathematicians. We're computer scientists, yeah. So the proof is not so important. Let every good thing starts with a let. A, F, N on N. a matrix, we denote with Mij, then n-1, n-1 matrix, we get from A by, I use the word deleting, if that's how you write it, the I row and the J column. For example, if A is, say, one, no, 2, 3, 4, 5, 6, 7, 8, 9. Then, for example, M11 is the 2 on 2 matrix you get from A by deleting the first row and the first column, which is 5, 6, 8, 9. Let's have another example. The same matrix A, but we look at, say, M32. You delete the third row and the second column, and you get 1, 3, 4, 6. And I do have the place here, so let's have another example. Let's say M32. Now you, what is M23? You delete the second row and the third column, and you get 1, 2, 7, 8. Yeah. Yeah. The matrix Mij for every ij is called the ij minor. That's how I call it. The ij minor. Now, one can calculate the determinant of A using the determinants of its minors. I want to say minor, but it sounds weird. With the following formula. Now, plus formula states that the determinant of A is calculated by sigma from 1 to n of minus 1, the power of I plus j, the ij element of A, and the determinant of the ij minor. One thing is missing on purpose. One thing is missing from the formula. Which index, who is running in the sigma? So, and that's a nice thing. very rare when it comes to mathematics. You can choose whatever I or J you want. Then second, the other index will be the one who runs in the sigma. And of course, you'll get the same result, whatever index you choose. So we can choose whatever I or J want, and then the other index will be the index of the sum. We get, of course, we will get same result for every way we choose. Let's have an example. We can use this matrix. Example, for instance, par example, calculate the determinant of A, let's say using or having I is 1. I can call it calculating the determinant, developing the determinant by the first row. Because so I specifically didn't write what is equal to 1 because we can choose whatever we want for I or for J, and then the other index will be the one who runs in the sigma, will be the one who equals to 1. Let's see in our example. Best way to understand is looking at an example. If we write down the determinant of A, and now the specific example is for this A, for I is 1, I plug in 1 instead of I, and then the index left alone to run in the sigma is J. I want to calculate the determinant of A. We already seen it last week. It should be 0. And then for the sport, say in Hebrew, for the practice, we'll calculate it differently. Let's say having J is 3 or something like that, using the third column, calculated by the third column, and we'll see that we get the same result. Yes, you calculate the determinant of A using determinants of the minors, which are matrices of order lower by 1. If you have, for example, a 6 on 6 matrix, the minors will be 5 on 5. Each one of them will require the determinants of minors 4 on 4, and so on. Now, when we have the determinant of A, let's write it down for our specific case. In our case, let's get down, see it. In our case, we have the index run from 1 to 3. I do it very slowly. When you calculate it, no homework or exam, such, do it right away. We have 3 elements in the sum. One for J is 1. Second for J is 2. And the third one for J is 3. Let's see if it fits in one line. If not, Get down one. Zikwa. Here. Remember. Oh, it's tomorrow, the 5th of November. Here. Just want to say, remember then what is the original matrix? Because we write it down, the font is big, the board is small, it goes away. Let's put it like it here. Let's delete it. This is A, so we can see it and use it. About what? No, it's V for Vendetta. It's a classic one. The movie.
We were there, okay, from like the guy in
Hugo Weaving. Ah, no, it's the actor.
No, I mean the mask.
He said his name. Guy what? Guy Fawkes.
Yeah.
Yeah. No. When it comes to the Israeli school, you should assume that we know nothing.
No, nothing.
No, it's a famous movie. It's a classic one. It's rated very high in IMDb. I don't remember the exactly rating, but it's above 8. It's above 8. So now, -1 plus 1 is just 1, and I don't want to write it down. A11 is 1 as well, just because it's a specific matrix right here, so I write 1 down. And we multiply it by the determinant of the 1 minor, which we get from deleting the first row and the first column. The first row is 1, 2, 3. The first column is 1, 4, 7. So you have 5, 6, 8, 9. Secondly, -1 to the power of 3 is minus. A12 is 2. And we multiply it by the determinant of the 1 through minor, which we get from A by deleting the first row and second column. It is 4, 6, 7, 9. Lastly, for this step, the -1 to the power of 4 is plus. A13 is 3. And the determinant of M13, deleting the first row and third column, is 4, 5, 7, 8. And as you mentioned nicely, the formula is recursive. We calculate the determinant of 3-on-3 matrix using the determinants of 2-on-2 matrices. Now, the determinant of 2-on-2 matrices, we've already seen them last lecture. It is the multiplication of the elements of the diagonal, and we put down the elements which are not on the element, so the diagonal. So we have let's have another line. 1 multiplied by 5 and 9 minus 8, 6 minus 2, 4 and 9 minus 7, 6 and 3, 4 and 8 minus 7 and 5. Trust me, bro, it's 0. So we already calculated the determinant last semester, last lecture, and I do this example every semester, so we know it's 0. Yeah. Yeah.
How is this formula? The formula exactly the formula last
Last week we talked about the permutations. Of course, it comes from the definition with permutations, but using definition of permutations can be very exhausting. We showed for a determinant of 3-on-3 matrix, there are 6 permutations and 6 elements in the formula. And when it comes to, let's say, 5-on-5, 5 factorial is 120. So this formula, it do becomes longer and exhausting by itself when the matrix becomes bigger. But when it comes, it's still easier, nicer, faster than the original definition. And secondly, we'll see, I wanted to, as I mentioned, I want to do it with less, with the third column or something for the practice to see that we get the same result and we can calculate it a bit differently. I want to show you that when we have a bigger matrix, let's say 5 or something, we can still use the fact that we can choose whatever column or row to develop the determinant with in order to choose the one with the biggest number of zeros. And when you have a lot of zeros, the calculation is easy. Yeah. Yes.
Like, what would be the iron?
If you choose the rows and columns to use correctly, you can calculate very quickly the determinant of even 10-on-10 matrices.
But these down looks like 5.
10-on-10 is legit. Easily calculated, of course, of course. We have, a full syllabus of 13 weeks, and you can't spend 3 hours of the exam on calculating one determinant. Yeah. I mean, you can. It will be very boring and very not examining what I'm trying to examine about. Let's, as I said, for the exercise, for the sport, for the practice, let's calculate it. Calculate it using J is 3. Now, let's calculate. Hey, having, for example, J is 3. I mean, if the matrix is 3-on-3, I can't choose J is 4, right? But every number between 1 and 3 is good. So this is the general way I wrote down the formula. But now I say, okay, let's plug in J is 3. So I, who little thing, is running in the sigma. And specifically, in our case, yet again, I take the matrix from here and put it in place. In our case, I'll just copy all this, and then I'll take down the matrix itself. In our case, we get the formula with a sigma from 1 to 3. Yet again, we have 3 components here. And I write it down very slowly, very lengthy. Don't have to do it when you calculate the determinant. How? Here it's in one line. What? What is it? We have I equals 1. Oh, it takes it away for some reason. So write down in different lines as well. I equals 1 and I equals 2 and I equals 3. Write down the exact numbers we get. Minus 1 to the power of 4 is plus. A13 is 3. And it should be multiplied by the determinant of the 1-3 minor, which we get from by deleting the first row and third column. It is 4, 5, 7, 8. Should always check me that I'm not wrong. It is minus because 2 over 5, 8, 2, 3 is 6. Multiplied by the 2, 3 minor, deleting the second row and the third column is 1, 2, 7, 8. The third one is plus, because it's minus 1 to the power of 6. A33 is 9, and the 3, 3 minor, deleting the third row, the third column, one gets 1, 2, and 4, 5. We know how to write this down when it comes to determinant of 2 and 2 matrix. We have 3, 4, 8, minus 7, 5, minus 6, 1, 8, minus 7, 2, and 9, 1 and 5, minus 4 and 2, and it equals to 0 as well. Source roughly broke, as I mentioned already. But I do it really quick in my head. Minus 9 plus 36 minus 27. Yeah, it is 0 as it should be. Any questions? So now, let's note the following thing. We can actually choose the row slash column we use to calculate the determinant. It will be easier, it is easier if we choose the one with most zeros, with the largest amount of zeros. Let's, for example, let's calculate the determinant of the 5 on 5 matrix. And let's have 1, 0, 0, 0, 0, 2, 4, 4, 5, 6, whatever. 3, 0, 3, 0, 0. And I'm trying to do it in my head so it would be easier. Let me change it a little bit. 4, 5, 5, 5, 5, and 5, 6, 6, 6, 6. But let's change it right now. Let's have set 0, 0 over here. I think it's fine. And I think it's enough for what I want to show you. So choosing the first row here, choosing the first row gives us, we call it A, I think. This formula, first row, it's just not n, it is 5. The matrix is of order 5. And every component of the sum contains 3 elements. One is the sign, third is the determinant of the minor, and the second, most important for my point, is the element of the matrix. 4 out of 5 elements of the first row, which we now use to calculate determinant, are 0. Which means that when you actually write down all the elements of the sum, the only one who is not 0 is the one who belongs to I equals 1, for I index 1. I mean, if you write down a J, excuse me. If you plug in J is 2, or 3, or 4, or 5, you get the element A, 1, 2, or 1, 3, 1, 4, 1, 5, which is 0 in this matrix.
Row or first column?
The first row. I chose the first row. I plugged in I is 1, and J, cool little thing, is left to run in the sigma. So we are left, it's J equals 1. And we want to write that this is 1 multiplied by the determinant of the M11, which is, of course, the determinant of M11. Let's put it already here explicitly. We have 4 and 4. We delete the first row and the first column because it's M11, and we get that. One thing is writing it leaks. Second thing is totally different. Is copying and pasting. Once you copy and paste all 16 elements here, where should I paste it? I think here. Yep. That is M11. I didn't missed out something. Let's write down why is it so. Because A1J is 0, except for J is 1. Only this little dude. So choosing the row / column with the largest amount of zeros makes the calculation very easy. Not very easy, easier. This would be so profound. Now, applying the same logic, which row or column should I choose to continue our process of calculating determinant? I should choose the second row, of course, which has the largest amount of 0. Now, we choose the second row, yes. And we are left with -1 to the power of 1 plus 2, because the element is placed in the 1, 2 interest of the matrix, multiplied by the element itself, which is 3, and multiplied by the corresponding null, which is 1, 2. No, it's 2, 2. So it is 2, 2 here is words of 1. My mistake. My bad. Another bad of mine is that I didn't ask the secretary if he can stay in this class for Infi, or at least in the same building. That will be fine. We're moving to the next building, so 604, and M22 is deleting the second row and second column. Let's see what we are left with. Um, at 0, 6, 0, 5, 5, 5, 6, 6, 6. And again, using our right or prerogative of choosing whatever row or column we want, of course, we're going to choose the first row. And choosing now the first row gives us 3, was already here from the previous step of the calculation. 6, let's say it's -1 to the power of 1 plus 2 because it's the element in the inverse of 1, 2. Yeah. What? Oh. Yes, but we still have a lot of ones. Zero. Ah, yes, good. It's a nice way to calculate it. When you have two rows, one is the multiplication of the other, the matrix is not invertible, which means the determinant is zero. Very nice. I want to show you the way of choosing the right row, so I'll continue with this process. I have 6 as the element and the determinant of the minor, which is row and column, each is 1, 2. So we have -18. What is left? Oh, 5, 6. 5, 6. And when it comes to a 2 and 2 matrix, it's simple. Notice multiplications. And it is, as you nicely mentioned, 0. Maybe we could already see it here. No, it's more complicated here, but when we actually have this row and this row as multiplication of one another, we know that the increment will be 0. Like it's changed the 6 for 7 or something like that. So don't be 0, but it doesn't matter. The principle is important. That's what I want to show you here. You can actively choose the row or the column you want to use in order to make it easier for you. Questions, comments, funny stories, jokes? Yeah. It's not the camera, it's the... I don't think that you are heard in the recording because you're far from the computer. One could try.
I just feel like it's that kind of technical stuff that I understand when I think of and not quite work.
Yes, why the formula is true, how do we derive it from the definition with permutations? I'm not going to show you.
Yeah, I know.
Don't have time.
Something that I have to do from like remember.
No, of course, you have the practice with Neil, which is very fun, I assume. And then you have your homework, which is even funnier. Then you'll get it in your head. I mean, I would say remembering it when it comes to the exam, it's easy. Let's see you forget it after the exam. If you actually solved enough exercises to be well prepared for the exam, it's hard to forget it afterwards. Not every formula is so important or stays in our heads, but the way of calculating determinants, you see that it will have its cameo appearances all along the course. It will be hard to forget how to do it. Okay, any other questions? So we took our time, we had fun, and we lost something like 20 minutes in the beginning. We're not going to finish all the material as it is in Andy's second lecture note, but we will start the next subject right now. We do have 10 plus minutes, and we'll continue next week, only if it will be okay, Bezrat Hashem. So, our next subject is called Eigenvalues. Values, Eigenvectors. In Hebrew, it's called vector עצמי וערך עצמי, value and vectors. The definition is simple. The math following definition is not always simple. Let A be a matrix F, N, and N. Scalar. It is customary to use the word, the letter lambda. I don't know why, but it is. Lambda in F is called an eigenvalue. I can bold the definitions here. On the board, it's a bit difficult to do. It's called an eigenvalue of A if there exists some V in Fn such that V is non-zero and multiplying V by A is the same as multiplying V by the scalar lambda. For a simple example, let's say we have a um, 2 and 2 is enough. Numbers you like? And daring today, aren't we? Okay. 2, and let's have a look at lambda is 3, and which V will give me what I want. No, I'll do it simpler since we are already late. Let's have here different number. No, enough. Which V? No, I'll do it differently. Let's have 2 here, and lambda is 0, and V, which V is multiplied by A and becomes 0. I'll write it down as a column, of course. The column becomes row. What's white? And let's have V as -2 and 3. No. -2, -1 and 1. Simply. Indeed, If you multiply V by A, you get 0 and 0. So that's 2, which is the same as multiplying V by lambda, which is 0, my example. So A is the matrix, lambda is called eigenvalue because you have this vector V, which the vector itself is not 0. Lambda can be 0. Maybe I'll mention when exactly lambda is 0. But you have the vector V, which is not 0, and the multiplication AV, the multiplication lambda V are the same. In such case, we call lambda eigenvalue of A, and V is called such V is called eigenvector. So definition itself is not so complicated. The first question, however, can have a full discussion about it, probably most of it the next lecture. How do we find such eigenvector values? And of course, the corresponding eigenvectors. The big question is always why? Why should we find it? Why is it good? Why is it important? But as we know, we are short of time and full of desire for the high salaried, high paying job after our Toal. So we are, first of all, we try to answer how do we find lambda and V, and then why do we find them? And we'll see it along the what's remaining from our course. It's very basic and important concept, the concept of eigenvectors and eigenvalues. I'll just say that whenever linear algebra is used in computer science and computer themselves, using matrices for graphic in computer games and processing images and whatever you want, the eigenvalues and the eigenvectors are an important part of the process. I think we will see it in our course as well, some different kinds of matrix decomposition, but it will be later. What I want to say in the 3 or 4 minutes we do still have is this. How can we find the eigenvalues of a matrix? We note, the question is, I have an A. How do I get this 0? Without a lot telling me so. And then the next question is, when I have this 0, how do I get the minus 1, 1? How do I get the eigenvector? We note that AV is lambda V is AV minus lambda V is 0. We can write A minus lambda IV is 0. If you multiply a non-zero vector by a matrix and you do get 0, it means, that's a knowledge from the first course, that the matrix is not invertible. Matrix, let's get down. So better. The matrix A minus lambda I is not invertible, which means that its determinant is 0. Of course, it will be in Hebrew. In conclusion, lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is 0. So, in order to find the eigenvalues of A, we solve this equation. Let's do it quick. Running out of time. In our example, quick. I want to find the eigenvalues of 3, 3, 2, 2. So, writing down A minus lambda I is actually writing down 3, 3, 2, 2 minus lambda multiplied by I, which is 1, 0, 0, 1. Here we actually have the determinant of 3 minus lambda, 2, 2, 3 minus lambda. Determinant of 2 and 2 matrix. We know how to calculate. Is 3 minus lambda multiplied by 3 minus lambda minus 2 multiplied by 2. No, I was wrong. Here it is 2, here it's 3. Didn't write it correctly. I was running. That's why I was mistaken. And here we have 6 minus 5 lambda plus lambda squared minus 6, which is lambda squared plus 5 lambda. So the eigenvalues. So the eigenvalues of A are 0 and minus 5. And again, we have a lot of questions. How many eigenvalues do you expect to find? What happens when the matrix is bigger? Do we always have such eigenvalues? How do we find the eigenvectors corresponding to these eigenvalues? Etc., etc. Of course, we'll answer these questions and much more on our next lectures. But yes, I wanted to give Nir something to practice with you about. So the definition and the way of finding the eigenvalues took more 2 minutes than I expected, but it's fine. Okay, so anyone has questions? Questions you want to be heard in the recording? You can ask me after I close the recording as well. If I stop the Zoom, you probably won't be able to see what I write. So anyone who writes down what I write, finished? Okay. Okay, so take your time. We're moving to 604, room 104. And I need to talk with the secretary if we can stay here Or we can
On Sunday, we have 4 lessons in a row, and all of them are either in 6 and 4 or 6 and 5. But because we have 4 lessons in a row, there's no reason why we can say one lesson the entire day.
um
On Sunday, so we have 4 different lessons. Well, they're all 1 after each other. Yeah. Don't worry about it. It's almost in math. I don't know if it's translated, but